qualitative arguments rather than explicit calculations. So, well, we start off thinking about non-renormalizable theories, right? And the how we understand most of the time how we deal with them is the Wilsonian, if you'd like, way of looking at it, which is, well, our theory must have some cutoff, and once we exceed it, we need to integrate in new degrees of freedom that make sure our theory is weakly coupled in this new regime, right? So for example, if we have the four Fermi theory, then which used to describe the weak interactions, once we reach high enough energy, then we see vector bosons, right? And this is very natural in the sense that it appeals to the intuition that as we have higher energies, we're able to probe shorter distances, and then new degrees of freedom become available to us, right? But the point that this paper makes, and it's motivated by, for example, the arguments from classicalization of the Grossmende paper that we've discussed, is that perhaps there's an alternative way of thinking about it, and it's mostly the idea comes from having this classicarizer field, right? So you have a classicarizer phi, which is sourced by in a way that so it has a given source, and the idea is that this source becomes big as you have high energy concentrated in your scattering, right? So, and this is very, well, in doing so, this source will force this classical field to become classical, right? And this idea that you have this big source that classicalizes your field isn't very new. For example, in Pedro's lecture from Zomologikov, we saw, I mean, the details are a lot different, right? But the idea that you have, as n grows large, this becomes very big, and this goes into a classical configuration, is somewhat familiar, right? Well, the idea then is precisely that. As you have this big scattering in for very high energy in this hard process, what you'll find instead of the perturbative divergence is that you expect in these types of situations you form these classical field configurations that and then you're forming these classicalons if you'd like that have some finite size, and what's going on is, well, once you have this classical configuration, the chance of it decaying back into a two-particle quantum state is extremely suppressed. So what you really have, so you're shielding yourself from having the problems that you'd find in 2x2 divergent scatterings in non-normalizable theories. And this idea is really, if you think about it, this sort of thing happens in gravity, right? Because if you have two gravitons that scatter they're very energetic, if you do it the field theoretic way, for 2-to-2 graviton scattering, you'll have something that's proportional to GNS, right? And this clearly violates unitarity for very high energies. But we know that in 2-to-2 scattering of gravitons, you won't have this sort of thing. You'll have two gravitons that scatter and become a black hole, right? And this black hole then later radiates photons that are very soft via Hawking radiation. So you're really connecting this long-range physics with this hard, with this very, very energetic processes. So if you'd like, the analogous idea here is instead of having this Wilsonian thing, what you have is as you grow in energy, you'll have this very big object that has some very, very high occupation number, and as such be approximately classical, if you'd like. So in a way, you're fooling nature, if you'd like, by having, instead of having, you have instead some effective coupling. So I don't know. That's very small, right? Because you're trading having these this very hard process by having this extended classical configuration. And well, the idea is nice, of course, but it's sort of hard to see how it would work, right? So I think it's instructive to look at an example. So let's look in at first a case where there's no classicalization, and this is phi-4, for example. So for phi-4, what you have is, for example, something like this, right? And it's right, and it's very important that it's oh, sorry, apologies. This should be here, phi-4, right? So in this situation, what you have at tree level to 2-to-2 scattering would be something like this, which will be proportional to lambda, right? And the cross section will then be an object like this. So this clearly tells us a picture that, well, higher energies means we have less and less scattering because we're effectively probing shorter and shorter regions. But let's look at it slightly different. Instead of looking at the theory at this level, let's think about scattering wave packets, and let's look at the equations of motion. So the equations of motion for this for this theory are just it's just this, right? And if what happens if suppose you have, for simplicity, at t minus infinity, very far away, you have these spherical waves. So that with very low occupation number, because we're trying to model these very to 2-to-2 scatterings, and they respect the free equations of motion, right? In this, and then let's try to solve perturbatively, right? So we can write phi as phi0 plus phi1. And once we plug this back in, what we're effectively trying to solve is an equation like this, right? So phi1 equals minus lambda phi cube, right? Phi0. And I won't really get into it too much, but as you have very high energies, what you find is that phi1 should be of the order of lambda over omega r phi 0, right? So, and this will define as some r star over r phi 0. So what's this telling us? Well, r star is effectively the distance at which scattering becomes relevant. So the particle propagates, the wave propagates up until r star. It propagates freely until around phi star when scattering becomes relevant. And this distance, as we expect, goes down with energy because r star is just lambda over omega. But let's look at a different situation now. Let's instead look at a different theory where instead of having quartic coupling like that, we have quartic derivative coupling. So, and this is very important because remember, if we want the system to classicalize, we need self-energy sourcing because we need the source to grow with the energy of your system in order to create these field configurations. So, right here you have this sort of thing here, right? You'll have something that's proportional to s squared here, right? If you try to do this perturbatively, as you'd expect, because it's non-renormalizable, you get some crazy amplitude that's proportional to L star to the fourth, omega to the fourth, right? So we're just using omega and energy interchangeably. And, well, but let's try to, if we repeat the analysis here that we did, again, the equation of motion is a bit more involved in this situation, but again, scatter spherical wave and look for when the scattering becomes relevant, what we find instead is something like this. Phi1 is proportional to r star over r cubed, phi1. And r star now is not the same r star as here. It'll be equal to L star square root, cube root of omega L star. This is very different, because what you have here now is that as energy grows, R star grows as well. So if scattering happens around, like I mentioned, around where S star, around at where S star, right, R star, right? So what this is telling you is precisely that there's classical information, because how do I put this? Well, the idea is, as your energy grows, if you want to actually probe 2 to 2 scattering, you cannot form these classicons because, like I said, they won't decay back to 2 to 2 states. So you need to do this very far away at R star. And if you do this at R star, then very far away, then momentum transfer is very low. And if momentum transfer, it'll be proportional to, I don't know, R star to the -1, because they're very far away. And this will restore, this is automatically inside the unitarity bound, because you've effectively shielded your theory from these very, very short, hard processes, very much like what happened with black holes. And a reasonable criticism of this would be that, well, perhaps does this hold when you try to do these localized wave packets instead of having these spherical waves? And as it turns out, everything still works. What you find is precisely the same idea. And interestingly enough, this is sort of your prototypical Nambu-Goldstone boson, because you have some phi, it's shift symmetric if you'd like. So there's some potential applications if you'd like to study these, for example, the standard model in some sense. There are a few ideas where you can try to find, if you can find some classical information there as well. And it's sort of a very interesting alternative, and it's, I don't know, that's sort of the idea, yeah.
Just to make sure if I follow. So the idea is that the proposal is that, I mean, you get UV completions. I mean, you suppose that the UV completion of the theory is dominated by, I don't know, classical processes.
Yeah, exactly. It's internal. It's people often call it self-completion as well, because it's really a system, a process where you don't need external degrees of freedom. The actual degrees of freedom of your original theory at these very high limits, they classicalize and they shield your theory from unitarity violation.
I see.
So, just to get, you made a comment connecting these last steps that you took with this black hole thing. I didn't quite understand.
So, when you have very, very energetic gravitons scattering, if they scatter close by, they'll just form a black hole, right? However, if you can in principle have the so this black hole will avoid, if you'd like, these divergences that you'd have from regular field theory, because it's just outside of what what it can describe, right? So here, the process is very analogous. If you'd like, R star can be interpreted analogous to a Schwarzschild ratio, radius of your theory. You're having, it's sort of analogous because you don't lose all access to the region inside. You just have formation of these classical fields. But really, what you have here, again, is you're scattering very high energy particles, and they're forming this classical configuration that if they get close to each other, they form this classical field configuration. So if you want to look at 2-to-2 scattering, you need them not to get too close to each other. And if they don't get too close to each other, then momentum transfer is very low, and then unitarity is preserved.
Can you explain that statement a bit slower about momentum transfer being slow and unitarity being slow? What exactly is it?
So,
Write an equation for one person.
well, I mean, it's not a particularly rigorous statement in the sense that it's not the idea is basically that if you have so if you have a process where it's easy the easiest way I find to understand this sort of idea is thinking about waves, right? So you have if you have waves that are very close by, they'll interact with each other and they'll swap a lot of momentum. But if they're very far away from each other, then by the time they interact in some region, the effect of their interaction is much duller. So they exchange momentum at much lower rates, and then by consequence, the if the momentum transfer is very low and proportional to this, and this again is inversely proportional to the energy, this is proportional to the energy, so the momentum transfer is inversely proportional here. What you have is basically that this this will not explode in the same way that you'd expect from regular perturbation theory, right? Because if you have, if the energy is very high, then and they're getting close to each other, you're just forming you're just forming classical configurations, right? So and then these describe multi-particle states which are not involved in this, right? Because they won't decay back to two particle quantum states. An equation for what exactly?
So so you are saying that the amplitude is not growing because you form a black hole. You
Well,
said this word.
well, yeah, I said that not in the same sense, right? Because you can't. What I said was not. I don't. Perhaps I expressed myself a bit imprecisely. What I'm saying is that this process of 2-to-2 graviton scattering, when there's very high energy, doesn't really happen in the same way, right? You can't have 2-to-2 scattering in the way you'd expect from field theory, because if they scatter in this very hard process with very big momentum transfer, you'll just find a black hole. So, and this, well, I mean, the fact that this is unitary, I suppose, is well, I suppose is by well, I mean, we know that this happens in nature, right? And we
But what equation describes that statement? You said that I have two gravitons and I scatter at very high energy and I form a black hole.
yeah.
So now I want to transform that into an equation, right? Because
Yeah.
in physics you need equations.
Well, I mean, you'll have very localized energy, so you'd have something that's you'll have some. It'll be more. Well, the energy will be enough to. So let me think about. What do I want to say?
The amplitude of 2-to-2 gravitons was a function of S and T.
Right.
Do you want to say that this function? Do you want to say something about the behavior of this function when S is very large?
Well, I mean, it clearly violates unitarity here, right? In this situation, right? It's unbounded.
But you are going to say something about what fixes this problem.
Yeah. Well, it's again. Well, The paper doesn't. It's more so. He does have a separate paper where he delves precisely into the gravitational idea of this. But my understanding of this is that it's analogous to this, where the black hole will you'll if the black hole is formed, then what you're probing is no longer 2 to 2 scattering, because this will just radiate. This will be, if you'd like to look at asymptotic times, then you're going from gravitons to very soft photons in the when at t equal to infinity when after this radiates, right? So the only situation where there's actual 2 to 2 scattering is when they're very far off from each other and you don't have you don't have enough energy density to form a black hole, if you like, and then you have and then this is the analogous situation to here, where you're only looking at true 2 to 2 scattering if they're very far away and you have low momentum transfer. Well. This one?
Yes. Would it grow or not with S?
At low momentum transfer, would it grow or not with S? Well.
What's the leading diagram describing 2 to 2 scattering of gravitons?
Oh, I've been, well, I'm not entirely sure. I haven't really done any low energy gravity field theory, quantum field theory. So, well, I suppose, well, I'm not sure what all the vertices look like, but
Why does it grow with energy?
why does this grow with energy? Well, because, well, if you'd like, Gn is inversely proportional to it has units of 1 over mass squared, right? So then if you'd like this to be dimensionless, then this must grow with energy. Squared.
Is an amplitude dimensionless?
Well, usually, yeah. Well, I mean, the absolute value needs to be some sort of. Oh yeah, you're right. It needs to be a probability density, right? So it can't be dimensionless if you the absolute value. It depends. Well, I mean,
And what you're scattering. But
okay.
so the more energy you send in,
Mhm.
the bigger this process is.
Yes, this one. Yeah. Right.
Yeah. So yeah, the exchange, if you have 2 gravitons, and if they just exchange a graviton,
Mhm.
that will behave as S over T. Because there is a
Right.
momentum transfer exchange. So yeah.
So something like that.
Let me ask one last question there. You did an estimate keeping one irrelevant term.
Here.
Yeah.
Yes.
But if you added the next irrelevant term, would it matter? This is the first irrelevant term you would write. Right? Now suppose I add one more.
Yeah.
Would it affect your computation?
Well, probably. Well, I mean, the point of this. No, the point of this. Oh, this should be 0. The point of this isn't to get a precise value for R star. It's more so to understand when the theory deviates from the free theory, or if, at first order. So it's not really relevant to think about second order contributions, because you're really just interested in when phi 0 is no longer a good approximation, and which is when scattering begins to be relevant, right?
you are saying is that if I have an effective field theory, at some scale, I get new effects and I don't control the approximation anymore.
Sure, yeah.
Not exactly the same as classicalization.
Well,
Saying
I'm not
at
saying.
that energy scale, that term is at the same order as the first term,
Mhm.
and therefore I need to keep it. But then I need to keep everyone at that energy.
Well, I'm not saying that this is. Well, what I'm saying is that this is a consequence. Well, this is a consequence of classicalization, right? It's perhaps imprecise to say that this is precisely classicalization because it's sort of a EOM analysis, but it's certainly congruent with the ideas that were proposed.
Okay, as I said, it's a speculative paper.
Yeah, it's very yes. It's
I work with it. Okay, very good. So let's thank. Please erase while I get paper.
sure.
I forgot to get paper.
Uh,
Som.
Very good. So let's get started with Rodrigo.
Okay. So the paper that I'm going to discuss today is that one there called High Energy String Scattering in ADS. And as usual, this paper is in the context of the ADS-CFT correspondence. And it deals with the following pair of dual objects under this duality. So we'll deal with a 4-point correlation function in n equals 4 super Young-Mills, which is a superconformal field theory. And this, using the ADS-CFT duality, should be dual to a closed string scattering amplitude inside ADS. So something like that. Where here we have closed strings. So, in a series of previous papers. This is a special set of operators in n equals 4, which are due to essentially graviton states in ADS. And in previous papers, Aldai and collaborators were able to use bootstrap methods in this correlator to derive, or in some sense, predict what should be the 4 graviton amplitude inside ADS in a near flat expansion. Near flat. This means that they computed the 4 graviton amplitude in ADS as follows. So just as in Tuesday, we know that the string amplitude will be an integral over the Riemann sphere. So listed 2t times a function which this is the function that appears in flat space, and we have an expansion. 1 plus x squared over r squared. Another function which we call W3 for reasons and I'm not going to explain. And another one, W6. And then we have an infinite series, and they were able to compute, using the bootstrap methods, these first 2 corrections. So one knows then the ADS for graviton amplitude up to order 1 to the radius of ADS to the 4th. And then we have some prediction from ADS CFT in some sense. And then it would be very interesting to compare it with an honest string theory computation in ADS. But it turns out that string theory in ADS is very hard to do. So instead of computing this full amplitude, the first thing to do is to take then the high energy limit of this and try to compare it with some computation in ADS. So take high energies, which means you take S going to infinity here. We also take R going to infinity, but with S over R fixed. That's the approximation we're going to do here and try to compare with the string theory computation in ADS. Just as we've seen in class, to compute the high energy limit of amplitudes such as these, which are integrals over the Riemann sphere, we can just look at the saddle point of this integral and then approximate it by the saddle point. And if this is equation 1, what one gets doing that is that 1 in the high energy limit is equal to the flat space for point. So flat space for graviton amplitude, which is the one we saw in class, for in the high energy limit, which is that exponential behavior, plus, again, a series of R squared, plus these same functions computed at Z0, where Z0 is the saddle point in this integrand. So there are, of course, other terms, but we don't know them. So that's what we can predict for the high energy limit of string scattering ADS from this CFT computation. What we can do now is let's go to honest string theory and try to compute the same quantity. So in this side, as we also seen in class, this should also correspond. This amplitude should be the following path integral, as Pedro shown. E2 minus some action, which is instead of the action for strings in flat space, is the action for strings in ADS, times the product of 4 vertex operators, which will should correspond to the graviton states. Okay, so in this action, essentially what we have in the action is, instead of the usual x mu of Minkowski space, we'll use some x big M, where M are the embedding coordinates of ADS, as I've shown in my first talk, and they satisfy the following constraint. So these are essentially the bosonic degrees of freedom, which we integrate over in this string theory. And since we're doing the high energy limit in this amplitude, we have to look for classical solutions of this action. And it turns out that the equations of motion are the following. So these are the equations of motion. And you can see from the form of the equations of motion that you can write a solution, x classical, in an expansion in 1 over r. So we have some classical solution, which is the solution in flat space, which we know from the class, plus curvature corrections which come from the fact that we are in ADS. And if we plug these ansatz in the equations of motion, it's clear that the equations of motion, we can solve the equations of motion recursively. Once you know x0, we plug this in the equations of motion, and you can match different powers of r in the correction, and you can get higher and higher orders in the classical solutions. And then you can solve the equations of motion and understand this high energy limit. And performing this procedure, what one essentially gets is that the ADS amplitude for 4 gravitons in the high energy limit should have the following behavior. Again, should be the A4 flat amplitude in the high energy limit times an exponential of s squared over r squared times a function of the variables which we'll call small v, evaluated again at the same saddle point. And so we have this equation, which is what we predict from CFT, and this, which is a string theory computation in ADS. What they've done, so what we can do now is compare. Of course, we only know the first 2 terms in the expansion in equation 2. We can expand this exponential and compare the terms in the expansion. And it turns out that this function, W3, is evaluated at the saddle point, it's equal to V evaluated at the saddle point. And moreover, and more non-trivially in some sense, this function W6 evaluated at the saddle point, it's equal to 1 V squared. So both results are consistent, and indeed it seems that if we were to keep higher terms in this computation, we would get exponentiation. And that's definitely a non-trivial agreement between the 2 computations. And that's their result.
Very good. Thank you for this.
Questions? Okay, João.
So here the z zeros are like the positions that we put the charges in Gross's paper, right?
Yeah,
But for all of the external states. So,
yeah, the punctures in the Riemann sphere. Yeah.
okay, and then in this case, the z zeros are what?
Are the critical points for which this integral is extremal, right? So
Oh,
that we
okay.
get a saddle point in this integral, a saddle point approximation in this integral over the Riemann sphere.
Okay, but then because here it has this intuition about it being the punctures of the Riemann surface.
Yeah.
So here I don't see the picture of the Riemann surface in this.
Right.
in
So
this
yeah,
case.
again, that's a CFT computation,
Yeah.
which is highly non-trivial. But it turns out that one can, how can I say, join these results neatly in something which reminds us of a worksheet.
Okay.
And more strongly, the results agree with the results from the worksheet. So, I mean, if these objects are dual, this representation should be possible.
Yeah, sure.
Then-
But there's no natural structure in the n equals 4 side that. So
No,
like
you just write down.
supposition in.
Let's see what worksheet representation of
Mm-hmm.
our objects
Okay.
that are consistent with the result we bootstrap. And then,
Thanks.
Questions? Egan has a question. Can you pass the microphone there, please?
In the string computation, do you compute the area of that surface, or is it other computation?
what you do is you get a classical solution, and you compute the action for this classical solution, which is the usual prescription to do saddle points.
And is it the area of that surface or not?
So, the action is the usual conformal gauge action. I don't know, dxm, d bar, xm. Where the? I guess it should be some kind of area. Yeah, it's like you pull back. I mean, the metric on the worksheet is flat.
Yes,
Yeah, it should be related. Like,
yeah. My question was because there is 1/r corrections. Then I don't know. It was not clear if. But okay, thanks.
I mean, if this should be an area, getting 1/r corrections should be related to having 1/r corrections in the metric, which would correct the distances of the small squares, in some sense, in which you're summing.
So I have a question. So in flat space, we know what energy is. What is high energy in ADS?
Yeah, I mean, if you're doing finite radius, you should look at the quantum numbers of PS224. I guess it would be related to the dimensions of operators. But in this computation, they actually also compute the momentum in 1/r expansion. So you have the usual momentum, which is conserved in the flat space limit, and then, okay, once I include 1/r corrections, this is not conserved. How should I correct this momentum in order for this to be conserved to order 1/r square? And they also do this game, perturb it.
So do they compute this function V?
Yeah, they compute it and show that they match.
That
It's
it
a-
matches
yeah.
that computation?
Yeah, it's like a polylog mass. Like this single-valued multiple polylogarithms, some combination of them.
So that computation of V, how does it go in ADS? So it's about expanding around the solution we saw in class.
Yeah.
Then you find this x1.
Yeah.
You plug it into the action, and this x1
Yeah, the
and
trick
then
is
you have
that,
to evaluate the action for this x1, and you find this function
yeah,
v.
exactly.
Just a bit confused by a few technical things. So here, why? What is z0?
Okay, it turns out that it is the same saddle point as in class, and they claim, I'm not sure I understand their argument, but they claim that's because all these functions are polynomials in S and T, and they don't change the place of the saddle point. But that's an argument which I wasn't able to properly follow.
Because I thought we are claiming that these terms exponentiate, right?
Yeah.
So if they exponentiate, why wouldn't it affect the value of the saddle point?
What? So, I mean, you affect the value of
Maybe
the
they are doing an
integrand at the-
expansion at small s over r.
Sorry?
Maybe it's still secretly an expansion in small s over r.
Small s over...
Or no?
I don't think so. I think S over R must be fixed. And I mean, the point is that the point in which you evaluate these functions doesn't change, but of course the integrand changes. But that's one important part of their argument that I thought about a lot, and I'm not sure why these corrections shouldn't change the saddle point location.
How does it work from the ADS computation? Why is, if they keep fixed s over r, all these terms should be equally important, right? So
Yeah.
is it true that x1 is a small correction when s over r is fixed, or x1 over r squared is as important as x0?
Okay. When you take this high energy limit with S over R fixed, some parts of X1 are relevant and some others are subleading. So there are terms like, the next term, subleading term in this expansion will be something like S to the 3 over R to the 5 times some other function, and it's subleading. And all other corrections are also subleading in the high energy limit. In some sense, yeah, this term is the only one that contributes at leading order in the high energy limit.
Okay. So this is a very non-trivial check for them, because they check that W6 at Z0 must be the square of W3,
Yeah.
which is a priori from the CFT totally new.
Yeah. It's a crazy function of polylogs, which turns out to match.
Okay, very nice. Okay, thank you. One last thing. Okay, who's next? Dennis, okay, very good. So, very good. So,
Okay.
please.
Can you hear me? Yes?
Yeah, it's okay.
Okay, so I'm going to talk about the problem that our Professor Vieira suggested last time. We have seen on the class that scattering process that we were studying was reduced to a problem to find a critical point, right? I will denote critical points by CP on this talk. So the main purpose of my talk will be to the counting of possible critical points that we have in our manifold. Okay, so to do that, we will consider the following manifold. We will consider genus G, which I'm going to denote by this. And well, actually, we have to consider a genus G for L particles, right? That we are, for example, the L charge particles are on the surface of this genus. Let's suppose that we have L charges then. Actually, we have to fix one of them, right? And once we have fixed one of them, we will remain with this manifold, right? We will have the Cartesian product of L minus 1 times this manifold. So I'm going to describe it briefly. First of all, we have also seen last time that let's suppose that I have a torus, which is like this. So in order to notice the minimum, saddle points, and maxima, we have to define some scale, right? From where we have to compare. I will denote this scale F. And well, we have defined by this F the minima points, saddle points, and maxima. And each of these points will have an index. The index will denote the number of independent paths that we can take, such that we are descending from each of these points to lower points on the manifold. For example, this point has no way to get a more lower in a more lower place, right? So we will denote the index by gamma. For this, gamma will be equal to 0. For these two, as we have seen, they have one way to get to a lower point, right? So saddle points have gamma 1, and the upper will have gamma 2, because its two independent weights will go always to, will leave you always in a lower point, right? Okay, with this we will define also a number which is C gamma, which is the number of critical points that has index gamma, okay? In this specific torus that we're considering, we have the following. C0 will be equal to 1, C1 will be equal to 2, and C2 will be equal to 1, right? But in a more general tori, with G holes, a genus, we will actually have 2G, right? Because for each hole that we have, we will have 2 saddle points, so we have to account for all of them. Now let's try to, with these numbers that we have here, let's try to find some way to obtain the critical numbers that we may have. A first guess that we may have is the following. We may expect that the total number, I will denote by this, the total number of critical points will be equal to 2 plus 2G, right? This is the total number of critical points that we have in a general genus. But since we have the Cartesian product of them, we will have to consider this case, right? We have to elevate to L to the minus 1. It's just permutation theory and that stuff. Okay, so we will try to get to this answer by doing some topological approach. First of all, I want to define which is known as the Betti numbers. To do that, again, I will consider the same torus. And well, I will define 3 numbers for this, and well, we will generalize then in a more general way. B0 will be defined as the number of connected components that we have for our manifold. So we have in this case 1, right? Because we have just one tori. I will define then B1, which will be equal to the number of circular voids that has our manifold. To verify the number, we have to set some cycles, which is closed loops, like this, for example. And as you can see, this one-dimensional path embeds some two-dimensional vacuum, right? So this will account to this number. Another possible path that has the same property is this one, right? That encloses this section. So we have that B1 is equal to 2. And well, we will define this the next one, B2, as the number of vacuums that are embedded or that are bounded by a two-dimensional surface. In this case, we have one, right? Because we have a tori. The tori has, it's inside is void, actually, right? So we have one. Again, we can generalize this for B3, okay? In this case, it will be equal to 0, but B3 will be something like a three-dimensional boundary that embeds a four-dimensional vacuum. As you can see, B3 and B4 are more difficult to draw, right? For a more general tori, we will have the following. For a genus G, we will have B0, 1, B1 equal to 2G, B2 equal to 1, and well, the rest will be 0. Okay, so why is it important to define these very numbers for our problem? It is important because with this, we can define something which is known as the Poincare polynomial. Which is actually some polynomial or some manifold in terms of x, which is composed by the Betti numbers as the coefficients of our polynomial. This will go from 0 to the dimension of the manifold. So for our case, in this case, we have, for example, 1 plus 2, right? 2x plus x squared. And for a more general case, we have to consider here 2g, right? The main use of this Poincare polynomial is the following. Consider that you have some manifold that is composed by the Cartesian product of two different manifolds. So it's possible to prove that the Poincare polynomial of this is given by the product of the Poincare polynomial of its components. So we have px and py. This is something very useful because it helps us to find the Betti numbers of a more general manifold, right? That's something that is very useful. In our case, we can apply this to obtain the Betti numbers of our system that we are considering, right? And well, we will have the following, right? By considering this, we will have that the Poincare polynomial of our L-1 product of genus G will be equal to 1 plus 2g x plus x squared to the L-1. So notice that from this, we can obtain the Betti numbers. What's the connection between the Betti numbers and the critical points? Well, it is connected by something that is called the Morse inequalities. The Morse inequalities, I will try to describe briefly, is the following formula. We have to add them until some value L, the following structure. We have here the permutated signature that our sum will have. Here we have the number of critical points on some index, and this will be always greater or equal than, again, we have here the permutated signs. And here we will have the Betti numbers. Well, actually, this inequality holds when we have that the L that we are considering as the upper limit of our sum equal to the dimension of the manifold that we are considering. As a consequence of this, it's possible also to prove a more specific case, which is the one that we are going to use. Ci, it's always greater or equal than Bi. And with this, it's possible to obtain the value, right? The total number of critical points as a sum of this Ci which actually will be, in this case, greater or equal than bi, right? And with this, we have a lower bound for the total number of critical points. So let's consider a specific case, which is given on the article. On the article, it states that we have to consider the genus 1, which is a tori, right? And we have to consider a system of 4 charges. Let's work with the first formula that we have found. With that expression, we can find that this replacing g equal 1 and this value for L, we have 4 to the 3, which is 64. And now let's work with this case. In the other case, we have to replace also, right, g by 1. The Poincare polynomial will be something like this: 1 plus 2x plus x squared to the 3rd power. And I will write the coefficients that this polynomial will have. It will have 1, 6, 15, 20, 15, 6, and 1. You can verify it very easily. If you add them up, you will obtain this number. The total number of critical points will have to be bigger or equal than. Here we have 30, right? Sorry, 50 plus 12, we have 62, 64. So we have obtained this, as stated on the article. However, there is something interesting about this solution. In this case, we have considered, to apply this formula, we have considered that it's possible to have, for example, if we are working with 2 different spaces of 2 different particles, to use that formula, we are considering also the case, or we are including the possible states that having, for example, 2 charges of the same place of the tori, which is something that it seems to be weird, right? But, well, in the article states that this kind of events, for example, could be important to mention if you are studying poles or the pole structure of the scattering process that we are talking about. But in this case, in the high energy limit, it's not very important. So they do not talk about that. One last thing that I would like to say is that this formula actually holds for any values of G and L. I cannot prove it analytically because it's kind of difficult to do this kind of measurement. However, I did some numerical computation and up to in a range of G for 1 to 2000, and also for L, and it actually holds. So that formula seems to be okay. That would be all.
Very good.
Mm-hmm.
Questions?
So this thing here, it gives you an upper bound for the number of
Yes.
critical points, right?
You can say that if we are considering, for example, the case that we have not to we are discarding this kind of configurations, right?
Mm-hmm.
So if we discard, instead of using this, we have to use another formula, which is with factorials and that stuff. So you can consider this as an upper bound.
And then the upper bound and the lower bound match,
Mm-hmm.
and then you get 64.
Yes, actually.
So does this always happen, or it's just?
Well, that's a good question. As I said, I tried to verify it for general numbers, but since it's very difficult to do it analytically because I have to expand this general polynomial, right, and zoom in all over its coefficients, I cannot prove it analytically, but I think yes. I'm not sure, actually.
What's the basic idea in to prove these Morse inequalities? What kind of math goes into establishing these inequalities?
Well, I couldn't follow very well what's the proof of these Morse inequalities because it seems to be a very complicated stuff to learn. connected to the RAM cohomology and that stuff. But some glimpse that I would give you is the following. Let's suppose that we have, I will draw it here. Let's suppose that we have this tori, right? And as we have seen, in this case, we have the equality of the Bethe numbers are the critical points. But let's suppose that instead of considering this configuration, I have something like a donut with some maxima here, and one local maxima, we can say, and these points. In this case, we have 2 additional saddle points, right? In this case, but we have not changed the topology of the system, so that would be the answer. That's why we are considering that, in general, we have to expect an inequality instead of an equality.
So did you establish this 64 because you have bigger or equal and smaller or equal?
Yes, that would be one way to look at it. Or, as we can see here, right? Since we are considering circular holes, if you want, we will always have the equal sign, right? At not that case. We're not considering this kind of case.
I got lost now. So this is the same topology as this, right?
Yes.
Are you saying that the Bethe numbers for these toros are different?
No, but the difference is the number of critical points of different index, right? That would be the difference between them.
So as you just explained now, it's easy to add more critical points without deforming the theory, because you can always put a bunch of maxima and minima, add more.
Yep.
So it's very natural that you have a lower bound on how many critical points, but it looks hard to have an upper bound.
Yes, exactly.
So can you explain what's the intuition for the upper bound? So the lower bound, I got. There could be some topology involved. But how did you get an upper bound? What was the logic for the upper bound?
You mean that the one that I have mentioned here?
Yes. Can you remind this?
Well, actually, it's something that I was thinking while I was trying to work with this. I was also wanting to establish some upper bound. And well, there is the way that I tried to explain this, as I said to Joao, was, for example, let's suppose that we are considering another manifold, which is 2 circles. We have to put 2 charges on these 2 circles. So let's suppose that we have this configuration, right, of being 2 particles at the same place. We have another one, right, which would be this, and the other combinations. To obtain that formula, we have to consider this configuration with looks to be odd, right? Because having 2 charges, 2 electrical charges at the same point seems to be non-natural. So instead of considering this, we just, to obtain the bound I have said, okay, so let's consider that only these kinds of states are possible. So if we consider this kind of states, we have to consider another formula, right? Which is in terms of factorials. So that would be less than this. But if we accept that these kind of configurations are possible, we have to consider all the possible states, and actually they are all the possible states that we can have in our total number of critical points.
So I understand that we have a map from L-1 copies to the complex numbers, because we fix one of the positions and we have L-1.
Yep.
But these equations are all coupled to each other. So when you draw a picture like that, where you have 2 decoupled spheres, how? They're not decoupled, right? The 2 particles interact with each other. The equations couple both. So why are you just saying I count one, then I count the other?
Because we are considering these critical points as a Cartesian product of the manifolds, right? It's like we are considering, we are integrating, I think, over these kind of surfaces when we do the the procedure that we have made to obtain the scattering formula, right? And each of them live on a proper space with some topology, in this case, a genus G. So we have to consider all the possible combinations of saddle points that we can have. So the stationary points will have the following structure, right? Let's suppose that I have some set of coordinates. For the particle one, I have to give some number, and the other one has to have another number, right? Let's suppose, again, 1 in this system, right? That's why I am considering the Cartesian product of this. So that's why I gave this the reasoning. Yep.
Okay.
Okay.
Okay, Francisco has a question?
Yeah. Yeah. So perhaps I missed a step when you were going through. So right behind you, how do you go from the having the inequality to the individual terms? Because I mean, if you have two terms, for example, then C0 minus C1 greater than B1 minus B0.
Mhm.
Oh no, never mind. It goes from one. Never mind. Never mind. Yeah. Okay.
Okay.
There are no more questions? Let's thank David.
Okay.
So last presentation. Would you be able to complete that while I get set up?
Hello.
Okay, let's have the last presentation by Aga.
So then my presentation, okay, it's about, can you hear me? It's about this Audet and Maldaceno paper about computing gluon scattering. So let's summarize what's gonna discussed. So we give a prescription for planar gluon scattering. Right. And this is gonna be a prescription using ADS-EFT duality, so gauge gravity duality. So, and moreover, the computation, it is done by finding classical solution. Related to classical solution of strings moving in ADS5. However, so this is related to Gross and Mende paper. but in EDS now. However, there is asymptotical behavior of these strings. And this asymptotical behavior will be precisely what I mean by prescription. So we will prescribe an asymptotical behavior of this string. So basically, what we're doing is computing scattering of glues, n glues, 1, 2, up to n. But if I want to use gauge gravity duality, I will do it in the ADS space, which has metric dx square plus dz square over z square, right? And therefore, this space, it can be, so this is the zx, and the point is that I will put a surface here along the z direction at the point zir, but this is zir is very large. So this is a D-brane. It's called a D-brane. And it's where open strings ends. So I have a lot of open strings in the bulk, in the gravity background here, and it ends in this surface at very large z. So then we will do a prescription that relates to the classical solution of these strings ending in this D-brane. And how does it work? You, first of all, have to consider each gluon to be gluon state to be associated to one strings. So these are the states. And what we're gonna do, we are gonna scatter these strings. So to do the computation, it's convenient to use T-dual coordinates. And these are defined as following. So the metric has the following form: dx square plus dot dot dot. Well, where dz is 1 over z square. And the T-dual coordinate y, so the T-dual goes from x to y. So this new coordinate is defined as the following. So by this equation. Good. So these are T-dual coordinates of the corresponding x. So the computation will be simpler. So the features of these T-dual coordinates is more or less of the following. So we know that there are conserved charges in the associated to each open strings. So if you parameterize it beginning from 0 and ending in the pi, so this will be the momentum, which is a conserved quantity. However, in the T-dual coordinates, it will be given by now an integration in the tau direction because of this epsilon. And the consequence of it is that y of 0 minus y of pi is equal to pi times k. So there is a widening in the z coordinates, in the y coordinates, which is not a physical, there's no physical interpretation, but it's only mathematical consequence of this transformation that will be useful. So this widening is just that we have a delta y here. And then using it, we are able to give a prescription. So as I said, we put a lot of strings ending here, but we must put the ending, the points in which so the first step for the prescription is that the strings ends in a one-dimensional line of this D-brain. So if I represent this D-brain here, so I put a lot of points, and I join these 2 points by a light-like line, but the 2 points are separated by a vector given by this distance here. So by this vector here. So if you want to scatter n gluons, we will put n vectors here. So Q1, Q2, and concatenate in order, so these are all light-like, and we concatenate in order to build a closed light-like loop. So this is a light-like loop. It's light. And then you have here in the D-brain. This is what I mean by asymptotical behavior, that the strings ends in this one-dimensional loop here, this one-dimensional surface, which is a loop, and therefore you have a surface in the rest of the coordinates, and also here in the T-dual coordinates, the metric becomes r square dy square plus dr square over r square, where r is equal to r over z. So if you want to study z very large, we are studying r very small. So now that we have all the asymptotical behavior, so this, first of all, this, the order that I put the points correspond to the colors of the gluons. Ordering. And the vector here corresponds to the moment of the gluons. So we have information about the color and the momentum. Then if we want to compute this, we want to evaluate it. But this is the same thing as computing a Wilson loop. So this is written in a paper by Maldacena. It's large N Wilson loops that they propose that this correlation is then this is a Wilson loop computation where C is the light-like loop that ends at r going to 0. And r going to 0 is the boundary of this metric here. So we are actually putting the Wilson loop at the boundary of the ADS. And this computation is, we know it is given by S classical, which is then as in the r square over 2 pi area, classical area. So then you know how to compute n scattering amplitude. You just put this light-like loop in the boundary, and then you have a surface. If you evaluate it, it gives an exponential of this area, and yes, and also this is a computation done in the boundary of ADS. So in the paper, they compute 4-point in order to check this. So they propose a line for, and they compute the area. However, this is infinite, so they have to use regularization. Kind of, if this is a p-brane, they regularize by considering a d minus 3 epsilon brane. And the result matches the theoretical consideration from quantum field theory side, given by Zwiban, Dixon, and so there is a paper in which they consider this computation, but not using ADS-FT, and they find a precisely match in the 4-point function. So that's what's the paper about. Thanks. Questions?
So you t-dualize the coordinates, and momenta in x correspond to these displacements in y,
Yeah.
right? On the other side, like if you were to look at momenta in y space, it should correspond to displacements in x, right? Because I mean, it's just
the condition on x corresponds to widening of y.
Yeah, but if the integral over the sigma of x corresponds to the tau of y.
Yeah, that's from definition of the
Yeah.
law. Okay.
So there you're taking like a static configuration of in the y space, right? Everyone is still, or am I wrong? Like there's no scattering, it's just strings ending at fixed places.
Yes.
Right?
Yes.
What is the interpretation of this in X space? Like why are the strings? What it means for the ends of the strings in Y space be like fixed, while in the next space we know they have a momentum, but this, I don't know.
Okay. So what's the interpretation? You mean that this is not moving, right? Okay. I don't know.
Maybe the question is stupid, I'm not sure.
No, but, well, what I can say, the Wilson loop to close, this things to close correspond to conservation of moment. So there is actually probably an interpretation, actually, but I'm not sure. I can't say anything concrete.
More questions? They don't need to be very technical. They can be more about the background as well.
So the only thing that you assume to compute the string theory side thing is the ADS geometry, right? Or what else do you?
Sorry, I don't. Can you repeat?
What are the assumptions that you make on the
String.
on the string side? Like, you just have to assume that you're computing an area in ADS, or do you have extra input from like it being type 2 or stuff like that?
Yeah, no. We just used supergravity solution like ADS solution. There is no type 2, and in the computation we don't just consider classical of the classical sigma model, actually.
So you compute some gluon amplitudes, and then you say that when you compute these amplitudes, you found some divergences.
Yes.
What's the physical meaning of these divergences?
It's because the area in ADS diverges, right? What's the physical meaning? Good.
Let me help you. As you point out, this amplitude can also be computed in field theory.
Yes.
And you said the result matches.
Yes.
Okay. So we have a scattering amplitude of gluons and it diverges. What could be the physical meaning of this divergence?
Something like IR divergence.
So what was good? So what's the physical meaning of this
Yes.
divergence?
Yeah, okay, good. Yeah, because there is an IR. Yeah, good. So at the beginning, you put Z, IR, finite. But you want to send it to infinity. That's going to be divergent. That will diverge. So it is, yeah.
Does the amplitude diverge?
No, amplitude can't diverge. The result is amplitude is A0 times IR divergence plus something else, something finite. Yeah, then you extract physical quantity from finite quantity.
So is the amplitude divergent?
No.
But you wrote some IR divergent.
Yes, it is divergent.
It is divergent?
Yeah.
So is an amplitude of gluons divergent?
Yeah.
Really? So does it explode the LHC?
Yeah, I think.
So are amplitudes of massless particles divergent?
Divergent.
What did we learn in the very first lecture about the amplitudes of massless particles? Are they divergent?
No, it's not divergent. You can always regularize it somehow.
Do you want to rephrase this word regularize? What do you mean by regularize?
Well, the quantity diverges, but from the infinite, you extract finite quantity, which corresponds to physical observable.
So are you saying that the amplitude diverges, but you will multiply by something that vanishes to get something finite?
Yeah.
Maybe truth is the exact opposite of that. Do you want to rephrase, to rethink your answer? So what's the form of this divergence? How do these divergences show up?
Good.
If you were to call lambda an infrared cutoff, how would these divergences show up?
Maybe logarithmically.
So if you do a one-loop computation, it's a log. I agree. And then you do 2 loops, is a log square, etc. And when you resum everything, what does it resum into?
Lambda.
Lambda?
Yeah, because exponential, right?
Just exponential of log?
Of mu.
What
La-
is,
No,
is that mu? Lambda is big or small for you?
big.
I don't care. It's big? Okay, so is that mu positive or negative?
Minus.
So is the amplitude really, are these log divergences indicating that the amplitude is exponentially large or exponentially small?
It's negative. It's
Right, so it's exponentially small.
Yeah.
So it looks like an infrared divergence, but it's really saying that the amplitude is very small. And we get a finite result because in the final state we can put many soft gluons. And when we add up those, there is a divergence with lambda to the plus mu. And then the two cancel, and that's how we get a finite result. So these divergences, they are physical. They are just saying that the amplitude is very, very small, such that to get a finite result, we need to sum over many massless gluons, many soft gluons. You see?
Yeah.
Okay. Why did we put the gluons at some very big ZIR? What is this very big ZIR?
Yeah, we are considering heavy, large momenta gluons. So if we put here, the proper moment is going to be large.
So you started saying, at the very beginning, the first thing I do is I put a D brain, and I'll put my gluons ending on this D brain, and this D brain is deep inside ADS at some very big Z. Why is this the right starting point?
Because this, okay. Well, my interpretation is that this is a IR like a cutoff, like a IR regularization, like actually, and then we want to consider gluons at large momenta. So that's why you can't put it here the cutoff very small. You want to consider very large cutoff.
Okay. Any other questions? Okay, so let's thank Hagen. Very good. So we are quite a bit late today, so let's move directly to discussing presentations. So make sure you have everyone written down so that you don't change your mind midway. Okay. Sim, sim. Obrigado. Pam, 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 pam. Okay.